I'm gonna walk up to this problem. I'm gonna look at it and say, hey, is it algebra, trig, or a mixture of stuff? Well, it's just algebra. And because we've been working on partial fractions, your brain might go, oh, hey, the bottom factors. But if we pause for a second and say, sure hope there's a u substitution in there, guess what there is? So if I come off to the side and I let u equal x squared plus 3x minus 4, and my du is 2x plus 3 dx, which happens to be what I've got on top here. Now, if you did this as a partial fractions problem, we should actually get exactly the same answer in the end, but I'm going to go u sub because it's going to be faster. So everything on top just turned into du, and everything on the bottom is u, which means that when I take that antiderivative, or the antiderivative of 1 over u du, I'm going to get back natural log absolute value of u plus a constant. Since this question was asked in terms of x's, I want to put it back in terms of x's for my final answer. And that is looking like the natural log of x squared plus 3x minus 4 plus a constant. Or if you took the time to do partial fractions, then to make your answer look like my answer, there's one little thing we have to do. And that is, if I factor what's inside of that log to look like x plus 4 times x minus 1, then using log rules, this can break apart to be ln of x plus 4 plus ln of x minus 1 plus a constant. So if you did this with partial fractions, I bet that's the answer you got. And if you did it with a u substitution, I bet this is the answer you got. But they're the same, so we're all good. Is to think about what e to the x looks like. So here is a graph of y equals e to the x. And I'm actually going to pull two different limits from this graph. If I look at the limit as x approaches infinity of e to the x, well, that's saying what's the y value approaching as my x approaches infinity. And that y value is approaching positive infinity. If I look at the limit as x approaches negative infinity for this same graph, as x approaches negative infinity, my y values are leveling off to 0. And both of these limits have a tendency to show up in our improper integrals. The other ones that show up involve natural log. So here's my graph of y equals ln of x. And if I look at that y equals ln of x graph, if I take the limit as x approaches positive infinity of natural log of x, this is going towards positive infinity as well, because those numbers are, the y values are getting bigger and bigger and bigger. Just other kind of facts to know with e to the x and ln of x, not exactly limit questions, but we should know that e to the 0 is equal to 1, and that e to the 1 is, well, just e. In terms of natural log, we should know that natural log of 1 is equal to 0, and natural log of e is equal to 1. Natural log of 0 is undefined, but we can talk about the limit as x approaches 0 for natural log of x. And that, looking at the graph, that limit is headed to negative infinity. And I want to define the area from 1 to 10. Well, as a definite integral, that would tell me to write the integral of 1 over x, here's my function, dx, and we'd be kind of thinking about this as a bunch of little rectangles that push as far to the left as 1 and as far to the right as 10. And then we'll use the fundamental theorem of calculus to say, I know whose derivative that is. That's the derivative of natural log of x. And then because it's a definite integral, I'm going to be plugging in the 1 and the 10. I'm going to end up with natural log of 10 minus natural log of 1. But ln of 1 is 0, and I get natural log of 10. We might imagine that, especially because this is calculus for biology, we often want to know what's happening far into the future. So if I think about this and go, oh wait, what if that wasn't 10? What if that was actually 100? Well, then my limits would go from 0 to 100. I'd take the antiderivative, get that ln, and we'd be going from 1 to 100, and then I'd plug in 100 here. Oh wait, but what if we wanted to push it out even further, like 100,000? Well, I stick some extra zeros here, which gives me a couple extra zeros here, and, well, dang, I don't really have enough space, but a couple extra zeros in here. And then we do the super mathy thing and say, wait, we didn't really want to go to 100,000. We wanted to go all the way to infinity. Because infinity isn't a number to put as a limit in our definite integral, we employ a mathy trick that we've been employing since 17a, and that is pick a letter and then use a limit to push that letter where we want it to go. So this would become the limit as b approaches infinity of what we just had for that antiderivative, natural log absolute value of x, evaluated from 1 to b. And this bottom step would look like the limit as b approaches infinity of natural log of b minus natural log of 1. And then here's the really, really unexciting part. The limit as b approaches infinity of ln of b is infinity. Yeah, there's an infinite amount of area under there if you go all the way out. Well, the first thing that we need to notice is that it is an improper integral because I've got that infinity up there. Like we were talking about last time, that means we're going to introduce a limit. So we're going to rewrite this to say the limit, and it doesn't matter what letter we choose. The book tends to choose A or B. So I'm going to let B approach positive infinity. And we're looking at this from 1 to B of 1 over x squared plus 1 dx. My next thing, I need to find the antiderivative of 1 over x squared plus 1. And this is where having all of those antiderivatives from page 345 memorized is going to be helpful. So this is the derivative of arctangent of x, which means my antiderivative of this is going to be tan inverse or arctan of x. So I've got tan inverse, and then we're evaluating that from 1 to b. Just like with any of our definite integrals, I'm going to plug in the top value and subtract off plugging in the bottom value. So I'm looking at the limit as b approaches infinity of tan inverse of b minus tan inverse of 1. Well, now it's time to think about what tan inverse means. So tan inverse of 1, if I've got tan inverse of 1, and I'm trying to find the value, That says if I take the tangent of both sides, 1 is equal to the tangent of which angle? So the answer to the arctan question is what angle gives us a tangent of 1? And the angle that gives us a tangent of 1, how about you type it in the chat? I'm going to assume everyone's struggling to figure out how to type pi. Well, you could type it as a pi, or let me get my alt code sheet out. Yep, I'm that dorky. Pi is alt 27227. Let me see if it works first. Type it in the chat. I'm looking at alt 227. Yep. Pi over 4. There you go. If you want to type a pi and you're on a computer, you can type pi by alt, hold down alt, and then type 227. Is that what I said? Yes, alt 227 gets you a pi. But the answer here in terms of the trig is that tangent of pi over 4 is equal to 1, which means arctangent of 1 is equal to pi over 4. Now this next one over here, finding arctan of infinity, remember that's asking us the question, if I really want to know arctan of infinity, that's saying tangent of what angle goes to infinity. And this one, I think is easiest by looking at a graph of tangent. So if I think about that graph of tangent, tangent has vertical asymptotes at negative pi over 2 and positive pi over 2. And it almost looks like a cubic in between them. So the angle where tangent is approaching positive infinity is pi over 2. So to evaluate this definite integral, I am now looking at pi over 2 minus pi over 4, which is pi over 4. And because we got a number for this definite integral that was an improper integral, there's an additional word that we attach to that, and we say that the integral converges. So anytime that we get a number as an answer for an improper integral, then we say that that improper integral converges. If when we're done we get an infinity, then we would say that it diverges. Here's the reason that I said it's really messy. If I'm going from negative infinity to positive infinity, then we're actually going to have to break that up into 2 pieces. So we haven't really talked about this, but when we're doing an improper integral, because we're going to have to write a limit, we can't have a limit. We can't like write 2 separate limit problems for the same integral. So instead, we have to use the property of integrals that allows us to break this up. So we can pick any number between negative infinity and infinity, any number at all, but usually we're going to choose 0. And I'm going to break this up from negative infinity to 0 plus an integral from 0 to positive infinity. Now, the other reason that I said it was messy, well, let me keep going for a second. Now that we have it broken apart, now each of these can represent a separate limit. So over here, I'm going to take a limit as a approaches negative infinity and replace my negative infinity with a. And over here, I'll squeeze in a limit as b approaches positive infinity and replace that infinity with a b. The next part, where I said life gets messy, well, life's going to get messy because in order to find the antiderivative here, I walk up to it and I say, is it algebra, trig, or a mixture of stuff? Well, it's a mixture problem because I've got algebra and exponentials. I'm going to pause, hope for the U substitution. Yes, we have a U substitution. I'm going to let U equal negative x squared. And that means that du is equal to negative 2x dx. I have the x dx, but I don't have the negative 2. So I'm just going to work with this first integral for a second here. And looking at this first integral, I know I'm going to have a negative 1/2 when I divide it over to the du. So I'm going to have a negative 1/2 out in front. But now I have to switch my bounds. And switching those bounds, well, actually, let me finish writing it first. So my x dx became a du. And e to the negative x squared becomes e to the u. But now I have to switch my limits of integration. So if I come over here, when x equals, so I'll have my x and my u. When x is 0, 0 squared makes my u 0. And when x is equal to a, u would be negative a squared. So when I change the bounds, I've got to keep the a where it is. So that'll be negative a squared and keep the 0 where it is. And we'll still have that limit out in front, that limit as a approaches negative infinity. Well, if I do the same thing with this second limit and we do that exact same u substitution, I'll have the limit as b approaches infinity. My x and my dx will become a, oops, didn't leave myself enough space there, will become negative 1/2. And then we'll have e to the u du. But we've got to change the bounds here also. So for this one, I've got my x and my u. When x is 0, u is going to be 0. And when x is b, u will be negative b squared. And I have to keep them in the same places. So the 0 is on the bottom, so I'll keep the 0 on the bottom, and the b is at the top, so my negative b squared will go to the top. Now we're ready to find that antiderivative. Well, the antiderivative of e to the u is e to the u. Keeping that negative 1/2, I'll have negative 1/2 e to the u from negative a squared to 0. And I've still got that limit as a approaches negative infinity out in front. Plus that limit as b approaches positive infinity of negative 1/2 e to the u from 0 to negative b squared. Next thing we're going to do is to plug in our limits of integration. So we're plugging in the top, subtracting off, plugging in that bottom. So I've got limit as a approaches negative infinity of negative 1/2 e to the 0 minus negative 1/2 e to the negative a squared. I'm going to run out of space. So cool. Plus all that stuff. All of this should be right there, but I'm going to run out of space if I try to write it. So instead, I want to go ahead and think about finishing off this limit, and then we'll finish off this limit. For this part, e to the 0 is 1. So I've got -1/2 times 1. Minus a minus is going to make that plus 1/2. And then here's the ugly part. So when I plug in -infinity for a, -infinity squared makes that a positive infinity. And then that one makes it a -infinity again. And e to the -infinity, we just had up on the screen a couple minutes ago, e to the -infinity is headed to 0. So that is going to be a 0. Questions about that limit? I talked through it, but I didn't write anything out. So I just want to pause for a second on that limit. Not seeing questions come up in the chat. So let's figure out the other limit. So now that we know what the answer is, I'm just going to write it really small under here. That part became -1/2. Now, let's look at this. So we've got the limit as b approaches infinity. We've got our -1/2 e to the, and now I'm going to plug in -b squared minus -1/2 e to the 0. Okay. I'm going to take that positive infinity and square it. So it's still positive infinity, but then make it negative. And e to the -infinity is going to 0. Minus a minus is going to make that plus. And e to the 0 is 1. So I've got a half. So I've got -1/2 from the front and a positive 1/2 over here. And my answer is 0. Wanted to find the area, for example, under, and let's call this function y equals nope. Why don't I make this y equals -x² minus 3x, which I think should factor as -x times, nope, I was right the first time, plus 3x, -x times x minus 3. That's how that ought to factor. -x² plus 3x, yes. Okay, so this graph matches that picture. And if I wanted to find the area under here, we've been practicing that for a while, that's going to look like writing that integral from, oh, well, we would need to know where it hit, but I gave it to us in factored form already, which means I know that that's at 3 and that's at 0. So I'd be looking for the integral from 0 to 3 of that, -x² plus 3x dx. Once in 6.1, we're introducing, well, what if I was actually trying to find the area between two different curves? So here, technically, we were also finding the area between two different curves. We just didn't really talk about it in that context. We describe this definite integral as representing the area under the curve. But technically, if we think about it, the area under the curve doesn't magically stop just because we hit the x-axis. The area under the curve would keep going. When we say the area under the curve, we really mean the area under the curve, but stop when you hit the x-axis. Well, what if instead of wanting that entire area, I actually wanted to come in and slice through this with another graph? Like maybe I had y equals 2x. Nope. How about y equals, well, I'll just make it y equals x. Let's say it was slicing in at y equals x. And I wanted to find the area in here. Well, there are a couple of different ways to think about this. One is to think about having the area under that blue curve, but kind of cutting it off right here, and sort of having this thing that's shaped like this, and then subtracting off this triangle part down here. And that should equal, visually, this part in here. Now, the way that we really do that algebra-wise is to say, if I come into this little section, and I know that finding the area under the curve, the way that we started this whole area thing was by slicing things into rectangles. So if I were to draw an arbitrary cross section for a rectangle, then I would get the height of that rectangle by looking at the height of my parabola minus the height of the line. So the height of the thing we're trying to figure out, the area of that strip, would look like a top minus a bottom for the height of the strip. And then I'd multiply that by our dx, or the base. So for this particular thing, I'd be looking at my top function, which is that parabola, negative x squared plus 3x, minus my bottom function, which was x. And then we would just have to figure out those limits of integration. And those limits of integration are going to happen at the intersection points. So here, thinking about, I'm going to take these slices, or these rectangles, as far to the left as 0. So I know I need a 0 for my bottom limit. But for that top limit, I need to know where these two functions intersect. So I've got negative x squared plus 3x. And to find the intersection, I'm going to set the two y values equal to each other. So I'm going to set that equal to x. Personally, if I've got a quadratic, I'm going to get a 0 on one side. And I never like to factor with negatives in front of my x squareds. So I'm actually going to push everything to the right-hand side. So if I add the x squared over, I'll have x squared. When I subtract the 3x from x, I'll have negative 2x. I can factor an x out and say these are going to intersect when x equals 0. That's the one we already knew just from looking at the graph. And when x equals 2. So I'd be evaluating this from 0 to 2. Given time, energy, and sufficient monetary motivation, I'm going to assume that you could finish that integral off. Okay. What we want to do is figure out the area in here. Yay. Okay. So if I'm trying to find the area in there, it's kind of an area that's trapped between these two curves, but also trapped by the x-axis. So if I think about drawing an arbitrary cross-section in here, if I think about drawing out some rectangles, the problem is, or rather a problem is, that when I go to draw rectangles in here, when I think about the rectangle that lives like right there, my top function is the red curve, and my bottom function is the x-axis. But if I move to have a rectangle over here, then my top function is the blue curve, and my bottom function is the x-axis. So to find this area in here, we actually have to split this up as two separate integrals. And I need to think about dividing it right down that line. So on the left-hand side, my integral is going to look like, oh, and I wrote it in factored form so that I would know where the intercepts were. So these intercepts are at 2 and at 5. And from the blue one we had before, I know that's 3 and 0. So when I write out my integral for the left-hand side, I'm going to be going 2 to something because we haven't found that intersection point. But I'd be using my function negative x squared plus 7x minus 10. I'm going to add that to this part on the right-hand side that's living underneath my blue function. And I'm going to go this time from that intersection point we haven't found yet to 3. And this function is looking like negative x squared plus 3x dx. And now comes the fun, finding that intersection point. I think I've chosen the numbers nicely, so it won't be that bad. Well, to find that intersection point, I'm looking for where these two y values are the same. So, or I'm setting them equal to each other. So if I take this, that negative x squared plus 3x, and I set that equal to negative x squared plus 7x minus 10, I tried to make it nice. If I add x squared to both sides, they go away. And I've got 3x is equal to 7x minus 10. So when I subtract the 7 over, negative 4x is equal to negative 10. It's a fraction, but it's not terrible. So it looks like x is equal to 10 over 4, or that's the same as 5 over 2. Or if you prefer that as a decimal, I am looking at 2.5. So that's my missing number here and here. It's going to be a 2.5.